Hello, welcome to this TED Talk about floating offshore wind farms. Humankind has always been well known for finding goals and innovative solutions against the different challenges that appear along the history, and so as with renewable energy. In relation to this, wind energy keeps expanding its horizons, this time overseas, no matter the water depth. The increasing energy demand and world population are two of the most relevant causes of global warming. It's true that during the past few years, renewables have increased their share in the world energy mix. However, coal remains on the top and constant, when it's also the most polutant energy source. In consequence, the review released in last October by the Intergovernmental Panel on Climate Change states the need to reduce temperature increase from 2 to 1.5 degrees in 2100. Otherwise, the ecosystem will be irreversibly damaged. To achieve this, it's important to reduce the emissions 45% in 2030 and reach the net zero in 2045 in relation to 2010 value. To face this complex challenge, offshore wind energy establishes as one of the most solid alternatives. The main advantages in relation to onshore are higher wind speed and frequency, no presence of obstacles that contribute to wind disturbances, and the big amount of free space. We are talking about the sea. However, over the last few years, engineering goes farther, betting for more powerful wind turbines, getting deeper and farther from the sea, from the coast. This promoted the development of a floating alternative. This technology can be divided into three aspects: platform, mooring system, and anchoring system. In terms of platforms, there are three concepts: spar buoy, tension-led platform, and semi-sub. Spar buoy is based on a cylindrical structure that acquires high stability because the gravity center is much lower than the floatability one. It's simple to manufacture, but its large drop causes some logistic problems during assembly, transport, and installation stages. For this reason, it can be used only about 90 meters depth. The second concept is known as semi-sub. Due to its short draft, it can be used from 40 meters depth, and it can be built in harbors, using just one barge to transport the system platform wind turbine to the placement. Nevertheless, more concrete and metal is needed in order to acquire more stability. Besides, active ballasts are partially filled with water are used to compensate weighting. Finally, tension-led platform differentiates from the previous one because on this occasion the mooring system is tense. However, the stress associated to these strains can jeopardize the anchoring system. In terms of moorings, the commercially ones are metallic chains or synthetic cables. They are not tense, but partially laid down on the seabed. This allows to reduce the charge over the anchors, which are mainly horizontal, and at the same time the platform has horizontal freedom to move a bit. Finally, there are three types of anchors. Dragging bed ones resist horizontal charge, while the driven field ones and suction are used when vertical and horizontal charge may appear. There are currently two wind farms of this type in the world: Hywind in Scotland and Windfield Atlantic in Portugal. The first one operates since 2017 and it's formed by 6 wind turbines installed over spar buoy platforms, while the second one has 3 wind turbines over semi-sub platforms. Besides, there are other 5 floating projects around Europe for the next few years, which demonstrates the development of this technology. So, after this short review, I would like to show you the potential of this technology with a practical case. And which is the best example to show for us? Yeah, it's Spain. Our country has a big offshore potential, up to 8 gigawatts. In addition, the continental crust under the sea is nearly non-existent, thus traditional offshore cannot be installed. And finally, it will help to close traditional thermal power plants. To evaluate wind conditions, we used the IDAE Wind Atlas, which is a mathematical model of winds. Based on this, we applied different filters to narrow down the areas to analyze. Firstly, we fixed the minimum wind speed in 8 meters per second, which greatly limited the potential placements. After that, we applied the environment regulation filters, ruled by Estudio Estratégico Ambiental del Litoral Español, and Zonas de Especial Protección para las Aves. The first one states also a minimum distance of 8 kilometers far from the coast. We can see how these reduce the potential areas. And finally, we use bathymetry to select areas above 60 meters and below 150 meters. In here we can see where we applied it, and here we have the potential placements that we needed to analyze in terms of energy production. In here we can see some simulations when we can see the energy production zones. These simulations were run using a Vestas wind turbine model V164 9.5. We can see how Rosa's placement produces less energy than Galicia and Cadiz. Regarding Galicia, the central area has the highest potential, highest production, with nearly 41.5 gigawatts hour per year. Nevertheless, the truth is that Cadiz has even higher production, and it increases as we go down south. In other words, we get closer to the Gibraltar Strait. Here, the maximum gross production is 42.5 gigawatts hour per year. Therefore, this will be the optimal placement to design this wind farm, 30 kilometers far from the coast and at a depth that is 90-100 meters. To conclude, it's worth to mention that this kind of studies should never be taken as theory, but put them in practice, at least some of them. In this way, we will continue aiming for a sustainable future and hence try to minimize the consequences of different mistakes that humankind commit every day against the Earth. Thank you.